So what you're seeing here is an absurdly powerful magnet, and I have a wire lying on top of it. In a moment, I'm going to momentarily run a ridiculously large current through this wire. Let's see what happens. And let's try it again. Okay, so you can see that whenever I run the current, apparently the wire is feeling a magnetic force. Now it goes without saying, don't attempt to recreate this one. Large currents aren't exactly a safe thing to do if you haven't been properly trained. And the magnet that I'm using here can really pinch you good if you aren't handling it correctly.
So in the demo, we saw that if you have an electric current flowing through a region of magnetic field, that wire was feeling a magnetic force. Now, electric currents are due to moving electric charges. So what's really happening is the moving electric charges, in this case the electrons in the wire, are what are actually feeling the magnetic force. Now, unfortunately, the way to describe magnetic forces gets complicated, and there's just no real clean way to get around it. It turns out that the magnetic force will be at right angles both to the velocity of the moving electric charge and to the magnetic field. So I'm going to go ahead here. Now I'll just start by drawing a actually, let me do it differently here. I'm going to start by thinking about a positively charged particle here. And let's say it's moving to the right. Now, what I'm going to be thinking about here is the product of the charge with the velocity. Now, since this is a positively charged particle, Q times V will also point to the right. There we go. Let's try that again. So Q times V is pointing to the right. So remember, if you take a vector, multiply it by a scalar, if it's a positive scalar, you get another vector that points in the same direction. If it's a negative scalar, for instance, if we're a negative charge, then it would point in the opposite direction. And let's just say that our magnetic field, we're pointing at some angle phi with respect to Q times V here. So it turns out that in this case here, the magnetic force that the particle would be feeling would be pointed out of the screen. So remember, the circle with the dot means out of the screen. And the magnitude of the magnetic force will be the magnitude of the charge. We're taking care of the directions with a vector rule that I'll show you in a moment. Magnitude of charge, VB, times the sine of the angle between V and B, or QV and B, it doesn't matter, it turns out. Okay, let's say this were a negative charge. So again, we'll have it moving to the right. In this case here, Q times V would be pointing to the left. My magnetic field would still be like that. These two angles phi are supplements of each other, so the sine of phi will be the same in both cases. And it'll turn out here that our magnetic force will point into the screen. Again, it'll be the same magnitude as what we were having before. So the way to remember this is to use the right-hand rule for magnetic forces. There's a bunch of different ways to do it. I'm going to be showing you how I like to do it.
Because the magnetic force is perpendicular both to the direction of the velocity of the charged particle and to the magnetic field, we have to use the right-hand rule to do that. You can see in this picture that I've formed the magic widget with my right hand. The way that I'm assigning it is that I put the force, force will go on my thumb. That's usually what we're trying to find. You'll align your index finger with the conventional current. So I for current goes with I for index finger. Conventional current is going to be the same thing as the charge of if you have a single particle, the charge of that particle times its velocity. And we will align the 3 field fingers with the magnetic field B. So a way to remember that is B field goes on the bird finger B to B. Another way that you can remember that is if you look at your hand from the back side, you can look across from your thumb to your index finger to your middle finger and remember to always tell a fib F-I.
Okay, so let's go ahead and work some examples here, just both to get some practice using the right hand rule and also just to make things a little more concrete. So let's say here we have a magnetic field that's pointing into the screen. Let's make it 1/10 of a Tesla. All right, and we'll start by having a proton that's moving straight to the right. So this is a proton moving straight to the right. Let's just start first by finding the direction of the magnetic force. So go ahead, pause the video, and get back with me on that. Okay, so in this case here, what you should be doing is pointing your index finger to the right, because this is a positive charge going to the right. That's a conventional current of one whole charge. It's a conventional current going to the right, so the I for your index finger should point to the right. While pointing your right hand to the right, rotate your hand around your index finger until your field fingers are pointing into the screen. When you do that, you'll get that the magnetic force points up along the thumb of your right hand. Okay, now we'll get to thinking about the magnitudes of this in a bit, but let's just try this again for an electron. So again, let's have an electron going to the right. Which way would the magnetic force point? Again, take the opportunity to actually do the right hand rule on this and see what you get. Okay, so now here, because it's an electron, V is pointing to the right, but that means Q times V would be pointing to the left. So we would be pointing our index finger to the left. Then you rotate your hand around your index finger until the field fingers point into the screen. When you do that, you'll get that the magnetic force points down. So now let's say for both of these that the particles are moving each at 1 million meters per second. let's go ahead and figure out what the magnetic forces would be. So the magnetic force, the magnitude of it will be Q, absolute value Q, V, B, sine phi, where phi is the angle between V and B. Now here, V is pointing straight to the right, B is pointing into the screen. So that's a 90-degree angle. So if you don't believe me on that, again, go ahead and make the widget. Point your index finger to the right. That's what QV is doing. B is pointing into the screen. Your field finger should be pointing into the screen. If you look at your hand, the angle between your index finger and your field fingers is 90 degrees in this case. All right. So this will turn out to be 1.6 times 10 to the negative 19 coulombs. We're going to multiply that by 10 to the 6 meters per second and 0.1 Teslas times the sine of 90 degrees. The sine of 90 degrees is 1. So 10 to the 6 times 0.1 is 10 to the 5. 10 to the 14 times 10 to the 5 is 10 to the negative 14. So in both cases, the particles are feeling a force of 1.6 times 10 to the negative 14 newtons. In the case of the proton, up. In the case of the electron, down. Now, the magnitude of the acceleration will differ greatly. By Newton's second law, F equals ma, the forces may be the same, but the proton is 2,000 times more massive than the electron. So that means that the electron's acceleration will be 2,000 times greater than the proton's as a result. Okay, so now let's think about this a bit more. Let's say that this is happening in a region where the magnetic field is big enough that no matter which way these particles are going, they'll continue to stay in the region of the magnetic field. In that case, what would be the trajectory of our proton or our electron? Doesn't matter. It's going to be a circle. And we can reason it like this. So this is the first of 3 cases I'm going to be thinking about of motion in a magnetic field. So let's go and focus on our positive charge. Just for a moment here, again, let's just have our magnetic field uniformly going into the screen like so. Now this first case that we're going to be taking a look at is when the velocity is perpendicular to the magnetic field. So in that case, we worked out that if this is a positively charged particle, say moving to the right like so, the magnetic force is perpendicular. Now, this means that the force being perpendicular to the velocity, remember from mechanics, that means that we can only change the direction of motion. We cannot actually change the speed. So it turns out that the path you get is a circle. And we can work out what the radius of this circle is. This radius, by the way, gets the name the cyclotron radius, which sounds really fancy. This comes from an older style of particle accelerator that still has some application in nuclear physics. where basically they were making charged particles move around in a circle using a magnetic field. And then by cleverly alternating an electric field at right angles to it, they could keep accelerating the particle to make it go faster and faster until it finally flew off to the target. So the cyclotron radius is just basically that was just how big does our device need to be in order to achieve the speeds we want. So in this case here, since we're moving in a circle, we can identify our centripetal force, in this case to be our magnetic force. Now remember, all centripetal forces are equal to mv squared over r. This will be qvb, and since v and b are at right angles, sine 90 is 1. All right, we're going to lose 1 power of v there. And we can cross multiply around to get that the cyclotron radius is mv over qb. In fact, what's often done here is you can do a variant of this where you can measure the mass per unit charge of a particle by taking a look at how the radius of a particle differs in a magnetic field compared to others. This is the basis behind mass spectrometry. Anyway, so that's what we get there. Let's go ahead and take a look at a case of, say, we have an electron. So let me just draw another magnetic field into the screen, like so. All right. So we'll go ahead, have our particle go like this. Now, you should convince yourself for a quick moment, if this is an electron here, so it'll be a charge of negative E. You should convince yourself that for the magnetic force to point toward the center of the circle I just drew, it must be the case that at the bottom here, my electron is going to the left. All right. Let's say we measure the radius that our electron goes as 2 centimeters. So 4 centimeter diameter circle, kind of typical. Let's say that we got this sitting in a 10 millitesla magnetic field. That's a pretty reasonable lab field strength. And what we want to know is how fast is my electron going? Well, I can take this result here and recycle it around to get the speed of my particle. I can get that my particle is going at qbr over m. Okay. And again, I should probably more rightly be putting in absolute value signs because we're handling our directions by hand here. So this will be the absolute value of negative 1.6 times 10 to the negative 19 coulombs. My magnetic field strength, we said, was 0.01 Teslas, and my radius is 0.02 meters, and my electron mass is call 911, so 9.11 times 10 to the negative 31 kilograms. This works out to be a speed of 3.51 times 10 to the 7 meters per second, which seems awful fast, and it is, but compared to the speed of light, it's about 11.5% of the speed of light. So this is actually, given how lightweight an electron is, this is actually a pretty reasonable number here. All right, so while we're at it some more, let's go ahead and think about the case of what the motion of our particle would look like. I'm going to call this one case 3. We'll jump back to case 2 in a moment. So in case 3 here is where V and B are either parallel or anti-parallel to each other. So this means they point either in exactly the same direction or in exactly opposite directions to each other. So in the case that we could be thinking about here, so let's say I have a magnetic field that is pointing up, like so. And I have some charged particle, and I'm not going to get fussed out about the sign here at the moment. Let's say it's going parallel, but it could also be going anti-parallel like that. So think about what the motion of our particle would have to be like in this case. Pause the video and get back with me. Okay, in this case, what we should be getting is that the particle is undeflected. Or in other words, it'll continue to just move in a straight line. And the reason for this is simple. The magnetic force is QVB sine phi. Well, here, phi is the angle between V and B. In this case here, that's 0. In this case there, it's 180. So you're going to put in either 0 degrees or 180 degrees in for your sine. Either way, you get 0. So in this case, it turns out that there is no magnetic force, which means that we're not going to be deflecting the particle. Okay, that's going to let me loop back to thinking about the more general case. So I'm calling this one case 2. This is where V and B don't have a special angle. So they aren't parallel or perpendicular or anti-parallel for that matter. We'll do it like that. P-A-R-A-A-L-L-E-L. There we go. So in this case, the motion, and I'm going to try to draw in 3D, and it's going to be a train wreck. The motion is going to be a helix shape. And the way you can think about it is some part of the motion is perpendicular. That bit's going to go in a circle. But some part of the motion is parallel. That part's a straight line. Now, if you imagine just taking your hand, moving in a circle, and then you start pushing your hand forward, you see that your hand goes into sort of a corkscrew motion. And the fancy mathematical name for a corkscrew motion is a helix. Now, this has application for a very pretty thing that you can see in northern latitudes, the aurora. So if you've ever had the opportunity to see the northern lights, here's what's happening. We have way over here somewhere the sun. This isn't even going to be remotely to scale. So way over there somewhere is the sun. Over here is the Earth. Now, the Earth has a magnetic field. It turns out to be due to charged particles being dragged around as the Earth rotates, as we've mentioned before. And the field will have a nice dipole shape to it, at least nearby. But what's going to happen here is, as it turns out, that charged particles are coming off from the sun. This gets called the solar wind. And they're just charged particles that the sun ejects. And just like we said that a magnetic field can cause the trajectory of charged particles to change, Newton's third law is going to require that the charged particles moving here can also deform the magnetic field. So what's going to happen is the charged particles, for the most part, will flow around the Earth, but they will have distorted the Earth's magnetic field in the process. So you'll get an area right here where the particles deflect around. That's known as the bow shock. Just like you see the shock wave coming off the bow of a boat. And then this point back here where everything reconnects is called the reconnection point. And this is the region where the Earth's magnetic field is distinct from the sun's. But not all particles will deflect, or charged particles will deflect around. Some of them will kind of fall in. And when they do, what happens is they will corkscrew along the magnetic field line. A magnetic field line. So, charged particle corkscrews EWS along the magnetic field line. Okay, so what will happen is it'll start corkscrewing around, and as the magnetic field lines get closer together in a treatment that's more advanced than what we're going to be doing here, this will cause the charged particle to feel a magnetic force that will reflect it. And so what will happen is the charged particle will slosh back and forth, following the magnetic field line, back, forth, back, forth, back, forth. If the particle is energetic enough, it can actually penetrate into the Earth's atmosphere. And when it does, it can collide with molecules in the atmosphere, causing the electrons in those molecules to get excited to a higher orbit. When the electrons in those molecules drop to a lower orbit, they emit light in different colors, mostly in the ultraviolet, but some of it is the really pretty colors that you see with the northern lights. Now, since the charged particles do corkscrew back and forth following the magnetic field line. This is actually how astronomers have been able to work out magnetic field strengths and magnetic field shapes for other planets. They can look at the auroral emissions from other planets as long as those planets have an atmosphere. And because they know that whatever you see being lit up in this part of the atmosphere up here, it has to have a friend down there as the particles keep racing back and forth along the line. That allows them to figure out both the strength and the configuration of the magnetic field. Okay, so in the next video, we're going to go ahead and take a look at the Hall effect and also talk a bit about forces on magnetic currents. See you in the next one.